Okay, our final example of partial fraction decompositions is how we handle a situation where the numerator has a higher degree than the denominator. So you may notice in this integram that our numerator is degree 3 and our denominator is degree 2. So we have to do a little bit of work before we can use any of the cases on our handout to set this up into a partial fraction. So I'm going to use some old school long division to set this guy up. This is one of the things I love about Calc 2. It's like, hey, remember that one time you learned that one thing in algebra and you didn't know why you needed it? Well, now you do. So anyways, here is some long division. I'm dividing x squared minus x minus 6 into the numerator. I placed a placeholder for 0x squared, and then I went ahead and did some old school long division. So in order to make an x squared divide into x cubed, I need a factor of x. Bring that around, and I get x cubed minus x squared plus 6x. Then I'm subtracting a polynomial, which means I need to change all of the signs. So the x cubes cancel, and then I will get a positive x squared, a positive 2x, and I carry down the negative 10. Then x squared times 1 will give me x squared, so I carry the 1 around, and that will give me x squared minus x minus 6, but I'm subtracting a polynomial, so I change all the signs. The x squared cancels and leave me a remainder of 3x minus 4. So what that really means is I can rewrite the rational expression x cubed minus 4x minus 10 over x squared minus x minus 6 as x plus 1 plus the remainder. So the remainder was 3x minus 4 over the divisor x squared minus x minus 6. What that also means is that I can split up my original integral. So now I can integrate x plus 1 dx, which is straightforward, and then I get to use partial fraction decomposition for 3x minus 4 over x squared minus x minus 6. But now you'll notice the degree of the numerator is less than the degree of the denominator in that second integrand, so I can go ahead and split that guy up. So we'll go ahead and do that. We're going to take a look at this integral right here and use some partial fraction decomposition for that. So now I have two linear terms in my denominator if I factor x squared minus x minus 6. So I can set that up to be 3x minus 4 over the linear factors x minus 3, x plus 2, equal to just the single coefficient a over the linear factor x minus 3, plus the coefficient b over the linear factor x plus 2. I'm going to clear the fractions and distribute a and b, and then group our coefficients by degree. So you'll see I end up with 3x minus 4 on the left, a plus bx as my linear coefficient, and then my constant is 2a minus 3b. So once I have that all set up, we should be getting used to this algebra by now. We'll go ahead and equate our coefficients and see if we can solve for a and b. So when we do that, we will get 3 equals a plus b, negative 4 equals 2a minus 3b. There's lots of different algebraic techniques to solve for a and b. I chose elimination. So I multiplied the first equation by 3, which gave me 9 equals 3a plus 3b, eliminated the b's, and I was able to solve for a equals 1. Plugged that back in and was able to solve for b equals 2. So with my new coefficients, I can go ahead and rewrite my integrand. So from my long division, the first thing I was able to do is write it as x plus 1 dx, and then that second term, 3x minus 4 over x squared minus x minus 6. Excuse me. So then we just spend a little bit of time solving for a and b. I'm writing in pen, I made that little mistake right there. So you'll see in the second line, it should be a over x minus 3 dx plus b over x plus 2 dx. And we solved for a equals 1, b equals 2. So my first integral integrates using the power rule to x squared over 2 plus x. My second one is a natural log, as is my third one with the coefficient 2. And so that's how we get our final solution